Welcome to the Ultralight Airplane Workshop. I'm Leon. It's been a few weeks since we did a design video for the UWS-1 Ultralight Airplane. So in this video, we're going to get back to that. Let's figure out what the aerodynamic load is going to be on the vertical tail. If you haven't been following along on the UWS-1 design so far, I'll put a link to a playlist up here in the upper right hand corner that you can click on, and you can go through all the design videos for the Ultralight. For figuring out the aerodynamic load on the vertical tail on the UWS-1 Ultralight airplane, we're going to figure out the span load and we're going to figure out the chord load. In other words, what the load is as we go across the span of the vertical tail and what the load is as we go along the chord. So in part one, first we're going to work on the span load. Then in part two, of course, what we'll work on is the chord load. Let me explain just a little bit more about what I'm talking about on span load and chord load. We got a little prop here that we can use. This was my first attempt at a plug for the UWS-1 Ultralight airplane rudders. So the span, of course, is going to be from a root out to a tip, and then if you're a wing, it's going to be even more. But for our tail, it's really just the root out at the tip. Now this is just the rudder, so there's going to be a vertical stabilizer in front of it, and the tip's going to go out just a little bit farther. The root is nearly the same on both. So what we're interested in this video is a span load distribution. In other words, how does the load change normal to this rudder as we go from the root out to the tip? Although we'll be calculating it for the entire vertical tail. Later on, we'll come back and do it for just the rudder. When we're talking the chord load distribution, we're talking about how the load is distributed from the leading edge to the trailing edge. On a span load distribution, a large contributor to the shape of that distribution is the plan form of your surface. Now, for example, on a rectangular, you're going to have your maximum load out here near the root. It's going to be fairly flat and then start curving off down to zero out the tip. On an elliptical, you're going to have a fairly similar shape, except it's going to be more gradual and fall off the whole way. It won't be a straight line, but more elliptical shaped. On a tapered wing, you're actually going to get something a little bit different. On a tapered wing, it's going to start out at a certain spot fairly high, and then it's actually going to come up to a maximum up around this area, and then taper off, similar to the way a rectangular wing would taper off. The more taper you add to the wing, the farther out that maximum position gets. And if you actually bring it out to a sharp point, your maximum is actually out here at the tip. And we talked about that on the planform videos for the wing of the UWS-1 Ultralight airplane in part one. I'll put a link to that up here in the upper left-hand corner. Let's go back to my office, get on the computer, and let's start doing some calculations and figure out this load distribution. We're going to start off with a few slides, doing some calculations and using values from previous videos in those calculations. We're going to use an old method that the FAA used to promote for coming up with aerodynamic loads on airplanes. Then we'll actually use some of our old data to calculate loads ourselves. After that, we'll switch over to using OpenVSP and VSPAero, which is a subpart of OpenVSP that is used to do aerodynamic calculations. Once we get that done, we'll have a span load distribution to do some other load calculations. What we want to do is calculate what the span lift distribution is at our maneuvering speed. So we'll get a maneuvering load on that vertical tail. Now, one way we can do it is to use some data that we've already calculated, particularly in the video for vertical tail size part 2. I'll put a video link up in the upper right hand corner to get a little refresher on what we talked about in that. Now, another way we could do it, well, not with the UWS-1, but another way that if you have a conventional configuration is you can use something from Appendix B of Federal Aviation Regulation Part 23. They had some nice charts and equations you could use to calculate vertical tail loads. Unfortunately, we can't use it for a twin tail configuration. So that's why we're going through and doing this calculation up here. But we'll talk about the FAA calculation first. We'll actually go ahead and go through it. The result that we want to have is the lift distribution load, which is the amount of lift that occurs at any point along the span of our vertical tail. And fortunately, the vertical stabilizer and the rudder have essentially the same lift distributions. We only have to calculate it once. And just a little refresher on what the UWS-1 tail looks like. This is the horizontal portion of the tail. I did not show the elevator here, but it goes in this area here. And then here are the twin vertical tails, and this is roughly where the rudder is on each vertical tail. Now our span that we're going to calculate is from roughly right here at the bottom of the rudder up to the tip. So that's what we're going to do our span calculation on. So to start with, let's quickly go through the FAA Part 23 Appendix B calculations for coming up with the vertical tail load. And I want to point out this is the old FAR Part 23 Appendix B. If you look at the 2020 version, Appendix B has actually been wiped out. It's now reserved. And I don't yet know what happened to that old information from Appendix B. I did a little bit of searching on it last night, but didn't find it. And if anyone knows, go ahead and put that down in the comments. Using that appendix calculation, we can come up with the design maneuvering wing load. And this load would be in something like pounds per square foot. Now, if you want to know what the total load is, you find the surface area of your vertical tail, multiply it by this number, and that would give you the total load. And here's the equation to use. N1 is the G load that we're going to design the airplane to be able to handle, and that's 3.8. W is the gross weight of the airplane, and S is the surface area of your main wing. If that value is less than 47, so basically 47 pounds per square foot, you use this equation. If it's greater than 47, there's another equation that you use, but I'm not going to bother talking about that. So the gross weight is going to be 548 pounds. If you want to know the details of where that comes from, go back to the first GC estimate video, and I'll put a link up here in the upper right hand corner. But a quick summary of it is that we're going to assume that the airplane is 254 pounds empty weight. We have a 250 pound pilot. We have a 24 pound parachute. And if I remember right, we ignored luggage. So I believe that was pretty close to what the value was. But like I said, this video actually has the details. The surface area of our wing is 91.5 square feet. If you want to know where that number came from, look at the final wing size video. And I'll put a link up here in the upper right hand corner so you can go back and look at the details for how we came up with that. There's actually several videos that actually precede this one, a part 1 and part 2 about wing size. And like I said, N1 is 3.8 from the flight envelope video. And now we want to know what the surface area of our vertical tail is, which is 6.89 square feet. And if you want to know how I came up with that, that is vertical tail size part 2 video. And again, a link up here in the right hand corner. And by the way, that is for a single vertical tail, but we have 2. And we're going to do all of our calculations for a single vertical tail. Just remember that there's another one too. And by the way, here is where we have that little determination I talked about up here. If this calculation is less than 47 and our aspect ratio of our vertical tail is less than 2. Now, ours isn't, so that's another thing that we fail on. Ours is actually 2.76. So our tail is a little bit longer and slender than what this is good for. So that's another reason why we're really not going to use this. But we are going to use it as a little sanity check. So it's worthwhile going through it. And again, if you want to know where that aspect ratio value came from, it's the vertical tail size part 2 video. So we do our little calculation here with the N1, the gross weight and surface area, and that comes out to 22.8. So it is less than 47. So if everything else was good, we would go ahead and use this equation. So if we plug in all of our numbers here, the 3.66 coefficient in front, the 22.8, which is this inside value here in this equation, we multiply that all together and we get 17.5 pounds per square foot. So that's the load on the vertical tail using the FAA Part 23 Appendix B method. So if we multiply that by our surface area, we have 126 pounds of load on that vertical tail. And that's just one vertical tail. So that at least gives us a value. We can do a little sanity check on the way we're going to do it analytically here in a moment. Now that we use the FAA Part 23 Appendix B method, the old Appendix B method, let's try to do a direct calculation where we calculate the load ourselves without trying to do an approximation like the FAA method is. We're going to choose a flight speed of V sub A to do our calculation at, and that's that maneuvering speed. Now, if you remember from the flight envelope video, this one here, where we got the N sub 1 3.8 G value, it's the flight envelope video. We calculated V sub A. V sub A is a speed where your wing of your airplane will stall before it has a structural failure, at least up to a G load of N1, which is 3.8 for us. So if you're flying at V sub A and you pull back on that stick as hard as you can, the wing will stall instead of getting ripped off. If you fly faster than V sub A, depending on how much faster you fly, you pull back on that stick real hard, you could rip the wings off. So if you're flying at V sub A or a lower speed, you'll stall before damaging the airplane, at least the main wing of the airplane. But you should also do that for your tail surfaces or any other structural part of the airplane. You don't want any of it to fail here at V sub A. It may fail at a higher speed, but V sub A or lower, you want it to survive, and that's what this little bullet down here says. We're going to design our V-tail so that it will stall before it structurally fails if we're flying at this V sub A speed. So we need to do our calculations right at where that tail will stall. Well, that's going to be the C sub capital L max, the maximum lift coefficient for the vertical tail. Notice this is a capital L, not a lowercase l. If it were a lowercase l, it would be section airfoil coefficient. In this case, we're talking about the coefficient lift of the entire vertical tail. Well, to start though with the section maximum coefficient lift with the rudder deflected 25 degrees, because that's a maximum deflection I'm currently thinking about giving the rudder. So once we have that, then we'll have to modify it based on our aspect ratio of our vertical tail to get what the vertical tail maximum coefficient lift is. Now this is a slide that I borrowed from the flight envelope video, and here's that V sub A. This is our maneuvering speed, and that speed is 73.1 knots. So we need to remember this value because we're going to be using it. All of our calculations will be at this speed. And here's another slide that I borrowed. This is from the vertical size video. These are various coefficient lift versus angle of attack plot for the airfoil that we're going to be using for the vertical tail. This is with the rudder deflected 0 degrees, so it's not deflected at all. This is with the rudder deflected 25 degrees. So for the section airfoiled, we get our maximum at about a 10 degree angle of attack, and it's about 1.65 for the coefficient of lift. I'm not going to go through the entire explanation of all this again. If you want to understand where all of this came from, which is converting from the section maximum coefficient lift to the actual vertical tail coefficient lift, go back and review the video on the vertical tail size. But essentially what we're doing is we're calculating what the slope of these lines are for the section, and then with this effective aspect ratio, we can go through a little calculation where we convert from this slope to the slope for the actual vertical tail. And it's going to be at a lower slope. And in fact, it's going to be at about half of what the original was. So the slope will be something like this. So maximum coefficient lift is going to be somewhere around in here for the actual vertical tail. What we want to do then is take the maximum coefficient lift that we got and multiply it by this little ratio, and that'll give us the new coefficient lift. So let's go look at that. Well, now it's time to plug in a whole bunch of values and figure out what that single vertical tail load is at our maneuvering speed. Now this equation, most of you should be able to recognize now. This is our lift equation. We've used it in a whole bunch of videos. You have lift on this side, surface area on this side, dynamic pressure here, and your coefficient of lift here. So we've used this on just about every flying surface doing calculations on either surface area or lift. let's talk about what we're going to plug in here for surface area, dynamic pressure, and lift. Like I said, we're doing this V sub A at 73.1 knots. Our dynamic pressure is this little equation, and I now use a spreadsheet to do this calculation instead of using a calculator where I can accidentally input the wrong values. And by the way, this row is at sea level, just in case you're wondering. So dynamic pressure is 18.1 at this velocity. The surface area we already talked about. This is the surface area of the vertical tail, 6.89 square feet. And now is where we're going to calculate the vertical tail maximum coefficient lift. So we're using that section maximum coefficient lift, and I said that looked like it was about 1.65. And then we're using that ratio to change the slope. That ratio is roughly half. You multiply these two together and we get 0.842 as the maximum coefficient of lift of a vertical tail when the rudder is deflected at 25 degrees. Well, now we have values that we can plug in to figure out how much load we have on our tail. So we calculate all of our wonderful numbers in here: surface area, dynamic pressure, coefficient lift, and we get 105 pounds. And before, we got 120 pounds using the FAA method. So we're really not too far off from that. And the FAA method is going to be conservative because it is a really rough approximation. It assumes that your tail volume is going to be with a certain range. It assumes that you have a conventional tail, which means you have your vertical tail in the middle of your horizontal tail and above it, with both the horizontal tail and vertical tail attached to the fuselage. That's the assumptions it's making. Well, we're completely different than that. We have the twin tail. We have rudders out on the ends of our horizontal tail. We have a higher aspect ratio than they wanted. They wanted something less than 2. So we really can't use the FAA method. So we're using a more realistic number. So I like this 105 pounds. So that's total load. Now we need to work on getting the span load distribution. And we will use this value in doing that calculation. What you're looking at here is half of the tail of the UWS-1 Ultralight Airplane. In fact, it's the starboard or right half. So down here, this is half of the horizontal tail. This would be the center line here. This would be over to the right-hand side, and this is the vertical tail. So the right-hand vertical tail. And as you can see here, this is where the rudder is. Now, I did not put the elevator in this version. Didn't want to have to deal with it. And by the way, what we're using here is OpenVSP, and the version is 3.21.1. There's a reason we're only looking at half of the tail instead of the full tail. We want to do a lift distribution calculation. If I was only interested in the horizontal tail, I would have everything out here, both the right half and the left half, and we would do our computation on that. And the reason that works is that OpenVSP calculates lift in the positive Z direction. And as we're looking at it here, that would be straight up. Well, our horizontal tail, we really can't calculate the side force on it because that would be in the Y direction, plus and minus Y. So what I've done is I've removed the symmetry from the horizontal tail, so only see half of it, and I've flipped it 90 degrees. Well, now we have a rear view of the horizontal tail, half of the horizontal tail. Here's that center line. Since I've rotated it 90 degrees, the horizontal tail is now vertical, and the vertical tail is now horizontal. Since VSPAero, which is what we are going to use to do our lift distribution calculation, calculates lift in the plus Z axis, we'll now be able to get a lift distribution across our vertical tail as we change the pitch. Now, it thinks it's pitch, but it's actually going to be yaw for us because our yaw is now vertical. To keep this video from getting extraordinarily long, I'm going to skip showing you how I do the setup and do the run. I'm only going to briefly summarize some of the settings and some of the results. That'll help us get through this a little bit faster. If you're interested in all the details, watching me go through the settings and the rationale for those settings, I'm going to make a tutorial for my builder tier patrons on Patreon. And in that, I'm going to explain this in detail, and you will be easily able to duplicate the procedure. If you try to duplicate it from what I'm going to show you here, it'll be a little bit difficult unless you're already familiar with OpenVSP and VSPAero. I've opened the VSPAero portion of OpenVSP. For the case setup, in order to get the lift distribution, we're using the vortex lattice method. I'm going to use my flaps, and I'm going to do 4 steps in changing alpha. But for us, since we've rotated 90 degrees, it's really beta for us. But the program thinks it's alpha, the pitch angle. Everything else I leave default values. And since we're limiting the deflection of our rudder to 25 degrees, that's what I put in here, and I've used minus 25, and that's to increase the camber even more in the direction of our change in alpha. Let me show you in a picture here a little bit better about what I'm talking about on pitch and the rudder deflection. When we're using that positive alpha, we're really meaning that the vertical stabilizer is pitching up. In reality, it's yawing to the right, but in order to get this calculation done, we're calling it pitching up. So the free stream air is coming in from the left horizontally, and then the rudder is deflecting down. So that increases the camber even more, increases the lift of the vertical stabilizer even more. Let's go ahead and run VSPAero and see what we get for lift distribution. All right, we now have our lift distribution. We have the coefficient of lift multiplied by the chord divided by our chord reference, which we had calculated up here automatically from the model. So this over in this area is our horizontal tail, which is now vertical. This distance from here to this distance here is the center line of the chord up to about right there, that curve right there. The rest of this lift distribution is from here out to the tip. Now looking at this curve is very interesting. I guessed at what this curve would look like back when I was figuring out the size for the vertical tail. Let's take a quick look at what I guessed at. So here was the guess on my rudder lift distribution, which is basically the same lift distribution as it is on the vertical stabilizer, fairly close. So here's what my guess was. From this area, which is that curve we were just looking at, it's down and then it starts lifting up and then comes back down again. So I was fairly close. It looks like the high point is a little bit further down than I was thinking. So this curve here isn't as sharp as I was guessing at. The actual curve is a little bit less steep. It comes down in this area. So here it is again. So this peak here is a little bit closer to the bottom, right in here. So the peak is about there. And this isn't quite as steep here. It doesn't fall off quite as steep. And by the way, I guess I didn't mention it, but these are the 4 angles. So as we increase in pitch, or in our case, beta, we get more sideways lift off of our vertical tail. As we're doing our rudder design and vertical tail design, in calculating how we're going to do the structure to deal with this lift distribution, we're really only going to start here, which is right here at this curve, and come out to the tip. The distance between these 2 horizontal lines is 5 inches, so we're really only talking about a 4-inch area. If you look at the average lift force along this 4-inch area, we're at less than half of what the maximum is. So let's just say it's half the force over a 2-inch span. I think we can probably ignore that. I'll think about it a little bit more, but I think we can probably ignore that. I wanted to verify something about this lift distribution. So I've gone and changed the alpha to negative. So instead of nose pitching up with the current configuration that we have, I'm going to pitch it down. So we're going negative alpha start, and then we're going to go to minus 16. We did plus 16 in the other direction. And then I also flipped my flaps around. Instead of minus 25, we're doing plus 25. So now what we should be doing is getting a lift downward instead of lift upward like we did before, given the current orientation that we have of our vertical tail. And again, let's take a quick look at a picture to understand this pitch and rudder movement. We're now pitching down the vertical stabilizer. The relative wind is still coming in straight and horizontal, and the rudder in this case is flipping up. The tail end is coming up, increasing the camber this way. So all of our lifting force is going to be in this direction, over this way. Now in the previous case, that free wind was coming in this way, so it was actually coming over the horizontal stabilizer before it hits the vertical stabilizer. Now it's hitting that vertical stabilizer first and only barely touching the horizontal stabilizer afterward. So we should see something different in our lift distribution. And I have the calculation right over here. I've made this window a little bit bigger so it's a little bit easier to see. Now you can see we're down in the negative direction for our lift distribution. It has apparently just about the same shape, just a little bit bigger. We were at about 1.4 when we were up here for this 16-degree angle of attack, and we've increased it to about minus 1.6. So in this orientation, we're getting just a little bit more force from that vertical tail, which is kind of interesting. But the shape looks like it's pretty much the same, but it's possible that peak is a little bit closer to the root. Well, I find that kind of interesting, so I am going to go ahead and use the lift distribution from this negative 16 degrees and from the positive 16 degrees. And we're going to do some comparison on those. Let's go to that now. Once you've obtained your results from the vortex lattice method, you can save them out. And you do that by clicking this export to CSV file. And CSV stands for comma separated variable. It's a text file. And you can actually import those into spreadsheets. Now, I've already saved out the results for both the positive angles and negative angles of attack. Let me show you that file real quick, but we won't get into details. So here is a portion of that CSV file that I've imported into a spreadsheet. The values we are interested in is this Y average. That's basically the Z position of our points. Because remember, we've rotated our tail by 90 degrees. So what was the Z axis is now the Y axis, as far as VSPAero is concerned. We also are going to want this coefficient of lift. I'd like to compare those. And we want this load distribution value we've been looking at. And let me just quickly scroll over so you can see that there's a whole lot of data. So looking at Y average, our positions stay pretty close to zero as we're going along the horizontal tail area. And then once we get up here a little ways, and up here, we are now at minus 4.5 inches. Our surface is moving along the negative Z-axis or negative Y-axis. Let's go back and look at that real quick. So 0 is right in here, and we're moving left, which is negative. So that's why we're saying that. And I am only grabbing the values starting at 4.5 inches and then on. And we go out to about 48 inches. So there's 48 inches. So that's just a portion of it, and this is the portion for the minus 16 degrees angle of attack. And I'm only interested in the minus 16 and the plus 16. So I've grabbed the rows that I talked about and stuck them into another spreadsheet. Here is the spreadsheet that I'm using to do some further calculations. So I brought the 105 pounds of load for the vertical tail into this spreadsheet because I'm going to be using that a little bit later. Another thing that I brought in that I neglected to mention from the CSV files is I brought in the chord for the vertical tail. Now the chord is going to be the same whether you're yawing left or yawing right, in this case pitching up or pitching down. And here are the 3 rows that I got from each of those CSV files. So I got the Z value, which is really the same for both of them. I got the coefficient of lift from each file. Another thing I got was that lift distribution line. Another thing that I did, since that lift distribution is negative when we're pitching down or pitching left, whichever way you want to think of it, is I took the absolute value of that. And then I can do a simple comparison between the left and the right. Then I also got the coefficient of lift values directly. And let's take a look at a chart here. So this is the lift distribution values. Here is the root of the vertical tail. Here's the tip of the vertical tail. So as you can see from this, at least in absolute terms, the negative pitching or left yawing has a higher loading than the right one does. That's kind of interesting. We'll need to keep that in mind as we're doing some design. So the worst case that we want to deal with is this higher loading. Let's talk about some of the other things we've been calculating. So I started some new calculations down here. So again, I copied the chord and Z values on these 2 lines. I'm not going to go into too much detail on a lot of this because the video is starting to get fairly long. What I wanted to do though is to repartition where all these Z values are. These Z values are determined by some settings in the geometry dialog underneath the section tab for a wing. Let's go take a quick look at that. So our tail is a wing, or at least half a wing. And if you come under the section dialog and take a look here under interpolated cross sections, you see this NU. For each section, you can set the number of lines that are crossed here. So there's a line, there's a line, there's a line. So wherever those are is where that Z values come from. But for some of the work I'm going to do now, I didn't want all this odd spacing on these Z values. I wanted uniform spacing. So I did some interpolation across these Z values, and I want to have a new Z value every inch. So starting at the -4.5 inch, every inch I create a new Z value by interpolating the old ones. And then at those new Z values, I interpolated a new chord. So with this new chord value, I came up with a new segment surface area. They're 1 inch wide in the depth of the chord, and I did that all along the vertical tail. It just makes it a little bit easier to deal with some of what we're going to do on down lower. So here's some calculations I did on the 16-degree up or right yaw, and then down here, the same kind of calculations, except it was down left. But instead of going through all these calculations, let's go down and look at some charts that actually display some of these values. What this is showing is the amount of lift along every 1 inch section of our vertical tail. And this is lift in pounds. So this kind of gives us an interesting lift distribution across here. And you'll notice that they're roughly at the same size. I normalized them so that both of them are lifting a total of 105 pounds. Before, when we were looking up here, we realized that in one direction we lift more than the other, but I wanted to normalize them so I could actually get a better idea of their shape relative to each other instead of their magnitude. So as you can see, on one of them, which is the down or left, it has less lift near the top of the vertical tail, but more lift down toward the bottom. But it's not a significant amount. It really isn't enough to drive the design of the structure much different between one or the other. Let's go ahead and zip over to the next one. For this chart and the next one, I'm treating the vertical tail as one piece, instead of being a vertical stabilizer and a rudder. In the future, after we've figured out the chord load distribution, I'll be able to divide these two charts up into a vertical stabilizer portion and a rudder portion. In this chart, we're going to treat the vertical tail as though it's one piece, and it's going to have one spar in it. And we want to know what the shear forces are going to be in the web of that spar. Over on the left, we're going to have shear force in pounds, and of course, down at the bottom, we still have Z position. Again, this is the tip, and this is the root. So the top of the vertical tail, the bottom. So as you can see, it runs from 0, as it should, out the tip, but down here at the root, it climbs up to the 105 pounds that we've calculated, and that's what should happen. That entire 105-pound side load on the vertical tail should show up as a shear force, 105 pounds shear force, down here at the root. And as you can see, there's not much difference on the shear force as we're traversing from the tip to the root, whether you're pitched down or left yawed, or whether you are pitched up, which is right yawed. And of course, that's that normalized. Both the left and the right have been normalized to 105 pounds load. And the last chart we have to look at. Again, we're treating the vertical tail as one piece instead of having a vertical stabilizer and rudder. And we're trying to figure out what the spar cap tension and compression forces would be on a single spar in that vertical tail. So that's what we're looking at here. In this chart, I assumed that the spar would be at about the 42% chord. I think that's going to be about right. And that makes it about 12% of the chord, since the maximum thickness is 12% at that 40% chord. This looks like a fairly typical tension and compression load as you go across the span of the vertical tail. Of course, there's no moment out here at the tip, so compression and tension are 0. So it rises fairly typically until it gets to about here. And then it starts to kind of taper off here at the end, which is unusual for main wings on an airplane. Now, given the load distribution that we have on this tail, I guess that makes sense. But let's talk about the absolute value. So down at the root, given that big bending moment we have almost 600 pounds of tension and compression in those spar caps. And again, in the future, I'm going to have to divide that between the vertical stabilizer and the rudder. I need to provide a few caveats about using the vortex lattice method. I talked about normalizing those lift distributions for a total load of 105 pounds. One of the things I really didn't talk about earlier was that for that left yaw situation, when I looked at what the total lift was that I was getting from the vortex lattice method, it was up around 170 pounds. But you can't really trust that number. We've got an angle of around 16 degrees. That's going to be up really close to what the stall angle of attack is. One of the problems with the vortex lattice method is that on the coefficient of lift versus the angle of attack, it is going to be basically a straight line, even past where that airfoil is going to start stalling. And the reason for that is the vortex lattice method has a few limitations. It doesn't take into account viscosity, it can't handle boundary layer separation, and it doesn't take into account turbulence. So it can't really model stall condition correctly. So it's always going to report a higher coefficient lift near the stall condition than you'll have in reality. Now you can trust it in the low single digit angle of attacks. It'll be pretty good there. And it'll be pretty good up until you start getting that round off on the coefficient lift as you're approaching stall. So the closer and closer you get to that maximum coefficient lift, the farther apart it'll get. And once you get past that maximum, the vortex lattice method really isn't reliable at all. So that's why I normalized those lift distributions for 105 pounds of lift. So we're getting much closer to being able to work on the structural design of the rudder and the vertical stabilizer on the UWS-1 Ultralight Airplane. But we have a little more to do. We've done the span-wise chord distribution. The next thing to work on is going to be the chord-wise load distribution. Once we get that done, then we can separate the load between the rudder and the vertical stabilizer. Like I said before, I cut out a whole lot of details on how to get data out of VSPAero into a spreadsheet and the calculations I did within that spreadsheet to get those charts that I showed you. If you're interested in those details, I'm going to be making a tutorial about how to do that, and I'm going to cut it up into several parts. And those tutorials on OpenVSP and VSPAero are going to be for my designer tiers on Patreon. So if you're interested in looking at those tutorials, there's a link down in the description to this video for the Patreon page for the workshop. Also keep in mind that I do post to the Facebook page for the channel, and I put pictures and little video clips of what I'm working on in there, so you can get a sneak peek of what's coming up on future videos. And again, there's a link down in the description for this video to the Facebook page for the channel. And in an upcoming video that won't be too long, you can see some metal that I have laid out here on the table. And this is going to be for a hotbox/oven to do post-cure on some composite parts and to form foam so that it'll match contours I'm going to have in my molds. See you next time.